Okay, so we did some problems where we used the definition of the derivative to find derivatives of specific functions. This problem, we're still going to be using the same definition, but using that in a little bit different way. So this time, we're going to be using that to show that a particular function is not differentiable at a specific point. So we're going to go through using the definition, but then also talk a little bit about why that's important and what that really means. Okay, so the first thing we want to do here is just start by writing down our definition. We're doing this one here at x equals 0, so I'll put 0 in for x when I write down this definition. All right, so don't want to forget the limit as h approaches 0. And this time we're going to have f of 0 plus h because we're trying to show this at x equals 0 minus f of 0 all over h. All right, and we're going to plug into this specific function. So I still have the limit as h approaches 0. And then when I put 0 plus h into the function, I will have the absolute value of 0 plus h, or you could just simplify that to be absolute value of h. We'll do that in a second. And then minus the absolute value of 0, which is just 0. All right, so let's do a little simplification here. Absolute value of 0 plus h is just going to be the absolute value of h. The absolute value of 0 is just 0. And so I end up with this limit. All right, so I need to think a little bit about, whoops, not 0 on the denominator there. That would be bad. All right, so I need to think a little bit about this limit. So one of the things that's important here is that the absolute value function treats numbers differently when I have numbers that are positive versus numbers that are negative. So we're going to consider both sides of this limit here. We're going to think about what happens when h is less than 0, and then separately we're going to think about what happens when h is bigger than 0. So I want to think about this limit when h is less than 0. We'll have the limit as h approaches 0 from the left of the absolute value of h. All right, so if h is less than 0, the absolute value of h will make that expression into a positive number. H is less than 0, h will be negative, and then the absolute value will change it to be a positive number. So it's changing the sign. That's what I've written here with the minus h. So when h is less than 0, the absolute value will change the sign. So it will switch the sign. That's what the negative indicates here. And so then I have the limit as h approaches 0 from the negative side of negative h over h, which simplifies to the limit as h approaches 0 from the left of negative 1. And that limit is negative 1. All right, and then if I think about the limit as h approaches 0 from the right, or when h is bigger than 0, when h is bigger than 0, the absolute values don't really do anything. We just get the same number that we put in. So I can replace the absolute value of h with just h. And this limit becomes the limit as h approaches 0 from the right of 1, and we get 1. And so one thing that we should notice here is that those don't agree. Negative 1 and 1 do not agree. So this overall limit does not exist. All right, so at that point, we've actually done what the problem here asked us to do. It asked us to show that the function is not differentiable at x equals 0. So we used that limit definition of the derivative, show that that limit does not exist. Remember, that definition says that's the derivative whenever this limit exists. So we've showed that that limit does not exist. I want to talk just a little bit, though, also about what this means geometrically in terms of what's going on with this function and why this is an important example to keep in mind. All right, so this particular function, you probably know what the graph of this function looks like. If I just draw an x and y axis here, we've got kind of a V shape to the function here. And x equals 0 is right here. We have the point 0, 0 there. And so if I think about what's going on with these two limits that we were looking at here, when h approaches 0 from the right, I have a point that's a little bit larger than x equals 0. So on the right side of x equals 0. And I'm looking at the slopes of those lines when that point is just a little bit to the right of h equals 0 and approaches 0. So as we get closer and closer to 0 and I look at the slopes of those secant lines, the slopes over there are +1. +1 slope. That's what this limit here means when h approaches 0 from the right. And then when I'm looking at the limit as h approaches 0 from the left, and I'm looking at these slopes here, I've got a point over here a little bit left of 0, and I approach 0, and I look at the slopes of all of those lines. Those all have a slope of -1. And so because they're not approaching the same value on both sides, that's why this derivative does not exist. So sometimes students say, I know that when I see a graph with a sharp corner on it, the derivative does not exist. The reason why is because of what's happening here. On one side, you're getting slopes to approach one value, and on the other side, you're getting slopes to approach another value. So the overall limit does not exist. This is an important example to keep in mind for a function that is continuous. The graph is connected here, continuous. There are no breaks in the graph, but not differentiable. A lot of students talk about this function when they think about a function that is continuous but not differentiable at a point.